start again the session, the afternoon session. Mm-hmm. Okay. So, so I will introduce John in English so that he can understand the bad things I tell about him. Okay, so John worked for 20 years in Maryland. Then he did also 10 years as a professor in the University of Toulouse in France.
Pas de ma connaissance, no.
Yeah. In the recent year, he has been visiting professor, I think, in Nice, but also in San Carlos for a couple of years, and he's actually quite involved as one of the main researchers in a project with Philippe Corteil on quantum sensors. In the recent year, he has been working a lot on scattering by sub-wavelength structures and metamaterials and plasmonics, and he will present his recent results about this.
Okay, thank you, Romain, for this this nice introduction. It's very nice to be here, and today I want to talk to you a little bit about some work which I simply do in collaboration. I'm retired now, so I'm not at Maryland, and I'm not at Toulouse, and I'm not at NIST, and I collaborate here. But you see, there's on my slides here, there's no logos, which means I have no institutional affiliations, really. So this is really just, now I do these kinds of things for the love of it, and so it's something of the work of an amateur. So what I want to talk about, though, is something which is a little different, maybe, from what we've heard up to now. That is the interaction of light, not at the atomic scale, and not at the macro scale, but at this kind of intermediate scale, this nanoscale, where the structure, the spatial extent of the structures with which the light is interacting is much less than the wavelength, but it's still much greater than the typical size of an atom. So we can still talk about extended, the properties of extended matter. We can still talk about index of refraction, which really does exist, I think. And permittivities, permeabilities, in other words, the constitutive properties of matter still is a valid idea. So since we're talking about the, oh my gosh, am I going to have this problem too? I hope not.
Switch off your wireless. It happens to me all the time.
Do you think it has to do with the wireless? You think it has to do with this thing?
Suppress the wireless.
Oh, all right. Well, let's see.
Well, it happens to me all the time. So
Okay, so, all right. So, okay. One moment, please. We'll go back here. And just go down. Problem is, there's a lot of things I don't see anymore. Okay, listen, I think I'm not going to fool around with this too much, because I'll try to talk fast, and so if I sort of move back and forth between these slides, maybe it'll keep it waked up. Okay, so anyway, we're talking here. We're celebrating the year of the light, and we've heard some historical chronologies or synopses of the development of light. But I thought it might be interesting to see exactly how light and matter how people have thought about it and considered it through the ages. So here in antiquity, in fact, in this area here, there really wasn't no one talked about the difference between light and matter. There was just something which was light and matter together. And in fact, in this regime where we had the Greek atomists and Empedocles, then Euclid, which had the first correct book of optics, and which had great influence in the Occident for hundreds of years afterwards, and then even up to Descartes. In this region, in fact, it was thought at some time that light was not something that came into the eye and was detected by the eye, but in fact light illuminated, things came out, corpuscles of light came out of the eyes and scattered off the world, and that's how we actually saw things. And then it was really at the time of the Renaissance, and then afterwards with the Luminaire, where we got a bifurcation in the 17th century, where Newton's theory involving mass and well-defined mass really changed the difference between what matter went off in this direction and started to be developed along this line, whereas light went over here. So over here, of course, we had Huygens said light is a wave. Newton was still saying it was a series of corpuscles, and so this went back and forth for a long time. Young interference gave great weight to this idea of light being a wave. Fresnel diffraction also added to it. And then we had Fizeau and Foucault had measured the speed of light. And of course, Maxwell was the crowning achievement with classical electromagnetic theory. In the meantime, over here, with Newton's idea of point masses and celestial motion, was developed the idea of atoms, the modern idea, not the old Greek idea of atoms, but the really new idea, which from experience, very careful experiments that were done in France and in England by chemists, the Lavoisier, who first saw that mass was conserved in chemical reactivity, Mendeleev with the periodic table, and then back in the late 19th, early 20th century, with Einstein's special theory of relativity, we see once again the concordance of mass and energy, and we saw with the Planck equation, finally we end up here where we can write mass in terms of two universal constants and simply a frequency. So here things, mass and light were together, and we find that back down here again, once more, as we go forward in time, that there's a very strong continuity or a strong identity between them. But what I'm going to talk about today, we can still make this difference, and it's going to be useful to talk about light and matter interacting as two separate things. So what the talk is basically about are the following things. It's essentially didactic with some new stuff down here. But basically what I'd like to do is introduce, especially to the students, the idea of what left-handed materials are, what is a negative index of refraction, and what good is it, what are metamaterials, and how they can be useful. Why are we still talking about plasmons? Every time I come down here and give a talk now, the last several years, I've been talking about plasmons, and they're still interesting, although plasmons, in fact, play a very important role, a crucial role, in metamaterials. So in addition to just being interested as a kind of electromagnetic surface wave disturbance at the interface between a dielectric and a metal, they also play a very important role in interactions between light and matter when these kinds of interfaces can be put into a periodic structure. And then finally, how do quantum dipole emitters interact with these plasmonic metamaterials? This is an attempt to try to get away from classical electrodynamics and to talk about some ideas about where the quantum nature of light may interact with these kinds of structures, these kinds of electromagnetic structures and material structures in a way which is both interesting and novel. So the work that I'm going to talk about here is that I'm going to discuss is in association with Philippe Romain, Euclides Marega, who, I don't know if he's here or not. There he is, there's Euclides, at the IFSC, and then also Ben-Hur Borges and his group in the engineering school at USP. Okay, so here's a primer on left-handed materials. What are they? Basically, let's start with right-handed materials, which almost everything is. This is what we're familiar with. And we know that if we have a propagating plane wave, say, that we have an electric field in one direction, the magnetic field is going to be orthogonal to it, and if we do E cross H with the right-hand rule, we find the direction of what the Poynting vector is, and the Poynting vector is going to be in the same direction as the propagation vector. So this is the normal situation, and the one that we're quite used to. Now, a left-handed material would be one which had still, E cross H is still equal to S. So we don't change the idea of what the Poynting vector is. But what is done is to say that the vector of propagation, the propagation vector, is now propagating in the opposite direction. So this obeys a left-handed rule instead of the right-handed rule. The K, of course, is just the velocity of light in the medium. It's omega over V. And V is equal to 1 over the square root of mu times epsilon, where mu is the permeability and E the permittivity of the material. Of course, when this is mu naught and epsilon naught, this is equal to C, the speed of light. Okay, so this is just taking this back up again. Looks like I'm going to have the same kinds of problems as we had earlier. So this is just here we have it again, what the velocity of light in medium is. And now this idea of the velocity of light in terms of the square root of mu and epsilon, actually, of course, the square root has a plus and minus associated with it. And the positive root implies right-handed materials, but the negative root implies these left-handed materials. Now, if this is something which is important to get down. If both permeability and permittivity, if they're both negative, then we must use the negative root. And this was first demonstrated by Veselago in his famous paper in Soviet Physics Uzbeki in 1968. Now, in real materials, most insulators exhibit both positive permeability and positive permittivity. So in that case, of course, we're dealing with ordinary right-handed materials. Ferromagnetic materials can exhibit negative permeability, but almost always positive permittivity. And metals exhibit positive permeability for most of the frequency range and negative permittivity. So basically, the kinds of materials that one encounters in nature have either positive permittivity or negative permeability, but it's very rare, in fact, never, does one find materials with both negative permeability and permittivity at the same time. So they simply do not exist in nature. Well, if that's true, then why are we even talking about left-handed materials? Well, it's not quite time to give up. If these materials don't exist in nature, okay, but suppose that they did, what would it look like? Theorists are curious anyway, so even though it doesn't look like these may not be realized, their properties might still be interesting anyway. So let's see what a left-handed material would look like if we had a slab of it. So here's a case, here's a very simple kind of structure. Here we have air, and we have a slab or a zone of this left-handed material. So this is going to have a negative permeability and a negative permittivity. And over here we have air again. And here we have just an oscillating dipole. And that dipole is going to oscillate, and it's going to emit waves in this direction. Now, here's a animation of what actually happens when the dipole encounters this zone of left-handed material. What you see is that the wave appears to be going backwards here, but the wave fronts, at any rate, are going backwards. But you'll notice that once we get out of that zone over here, these waves are now progressing still in this direction here. So it looks like in this direction we have some very weird kind of behavior, and this is often characterized by negative index of refraction. And the question is light really going backwards here, or what do we really mean, or what do we think about, or how can we think about this problem? Now, the way that that last animation was actually done was in the following way. I constructed an artificial material where the permittivity and the permeability came from resonances, and I sort of made the material so that it had a negative, a dielectric, or an electric resonance, or electric dipole resonance, and a magnetic dipole resonance at the same frequency, and then constructed things so that this negative branch here, where it goes slightly below 0 for the permittivity and for the permeability, is such that we have at this wavelength an epsilon of minus 2.5, a mu of minus 2.5, and so the n, which is the square root of epsilon mu, this is the index of refraction, is minus 2.5. So this constitutes a negative index of refraction material, and this was first popularized again, or resurrected from Besilagos' paper by John Pendry. I think it was either in the year 2000 or the year 2001, where he wrote a very provocative phys rev letter called Left-handed Materials Make a Perfect Lens. Okay, so even if left-handed materials do not exist in nature, is there some way that we might be able to see some of their effects? So it looks like the effects would be interesting, but is there some way that we can kind of mimic or get around the idea that in real life or in real materials we don't have simultaneously negative mu and negative epsilon? And the answer is maybe, if we take a closer look at how light really interacts with matter. Now it turns out, of course, as you well know, light waves consist of frequency, phase, propagation direction, and polarization. So wave solutions to Maxwell's equations can be divided into transverse electric and TM polarization. So I would like to turn it off, but the problem is I can't, with the screen set in this way, the place where I would turn off the wireless, I can't even get to. So I'm afraid we're just going to have to live with it. So I'll try to go as quickly as possible. But anyway, this is for students. The idea here is to indicate that this division into TE and TM polarizations is the key to being able to go a little further with this idea of negative index. So this is what TE really means. You imagine that you have light coming down, impinging on some material. We have a plane of incidence, and you see the electric field is going transverse to this plane of incidence, and that's why this is called transverse electric. There's another way of arranging things, though, where we have the axis of propagation is still the same, but now the E and the H have changed signs, so we have now a transverse magnetic vector, and so this is called TM polarization. Now, these kinds of, another way of writing Maxwell's equations in terms of these TE and TM polarized is just this way. So what we find here is that we see that we have a relation between a spatial derivative of a component of the electric field, which depends on the permeability times H. Here we have another factor which just depends on epsilon, and another factor down here which is mu. Now, in this set of equations, this TE polarized set of equations, we see that in this one in particular, we have the difference between two spatial derivatives, and that's the one that only depends on epsilon. Down here, it's the mirror image of that. Here we have, we just exchanged E for H's. We see we have two equations involving the permittivity and one equation involving a difference between these two terms only with mu. Now, at sub-wavelengths, it turns out that if we take a look now at TM polarization, this is the only term that involves the permittivity, the permeability, excuse me. And this one, these terms in the sub-wavelength scale are this one is going to be very small compared to these two, and so we can drop this term. And so therefore, Maxwell's equations are being controlled by these two equations, this one and this one, and they only depend on the permittivity and not the permeability. So in this sub-wavelength regime, the TM waves depend not only on permittivity, not on permeability, and negative permittivity materials do exist in nature. They're metals. And so therefore, sub-wavelength structures can produce an effective left-handed material. So here's an example of one. Supposing that we have some dielectric in here with a given epsilon. We have silver on each side here. We have a source that comes up here. And this T here, this thickness, is going to be some sub-wavelength thing. So we imagine now the source is going to be an optical wave somewhere in the optical region, so 700s, 500s, nanometers, something like this. And this T can be something on the order of 20 nanometers or 25 nanometers. So what kind of waves are going to be set up in this kind of structure. This is going to be essentially a waveguide, and so we can talk about modes of that waveguide. And the modes of the waveguide are really all described by this rather complicated and dense slide. I'm only just going to talk about some of the features of this slide, and the idea is for you to think about what the structure looks like. At the same time, we're looking at these important traces. So basically, the first thing to notice is that there's going to be two kinds of modes that are propagating in this kind of gap structure. There's going to be anti-symmetric modes. This is the silver on each side and the dielectric in the middle. There are going to be anti-symmetric modes that look like this, and there's going to be symmetric modes like this. And we're looking at HY now, because remember this is TM, which means that there's only one component of the magnetic field, and so it's a good idea we can just treat this as we don't have to worry about components, there's just one of them, so we think of it as a scalar. So 25 nanometer, and we're going to have these two kinds of symmetries for the modes. Now over here, this is the dispersion diagram for these two different families of modes. So it turns out all the anti-symmetric modes are on this side, and what are we plotting here? This is KZ, this is negative KZ. So here, this is the KZ, which corresponds to a propagation down here in the negative Z direction. On this side, we're talking about modes which are a positive KZ. So the phase velocity is just given by W over K, so which means the phase velocity for negative K is going to be in the negative direction. Vg is the group velocity, which is d omega dk, and we can get both the phase velocity and the group velocity off these dispersion diagrams. So in this quadrant, for example, we have positive index waveguides because we have both positive phase velocity, and we have the slope of this line is the group velocity. So we have positive phase velocity and positive group velocity. Over here, we have, in this quadrant, we have negative phase velocity, but positive group velocity. Now, the positive group velocity means that's the direction that the flux goes, or the energy flux goes, and the phase velocity is the direction that you see when you see the waves propagate. So this is what an anti-symmetric mode actually looks like. So here you see the blue is negative and the red is positive, and so this is the amplitude. You see that there's a node that goes right to the center here. This is an FDTD numeric solution for HY for a negative index anti-symmetric mode for 500 nanometers. This is 25 nanometer gallium phosphide and real silver on each side. So you can see that this is a typical kind of waveguide mode. It's anti-symmetric, and if we actually see how this is actually how this thing propagates. Now you'll notice that first of all, obviously, the phase fronts are moving downwards in the negative direction, just as we expected. But you also see that the amplitude down here is much, much higher than the amplitude up here. And that, in fact, that's because this is real silver, so it means it's lossy. So the light which is starting in this direction is actually the group velocity, or the pointing vector, is still moving in this direction. It's still dissipating in this direction, even though the phase velocities are moving down in this direction. So there's a crucial difference between group velocity and phase velocity, and it's in fact most of the interest in physics is with the group velocity and with the direction of S, the direction of the pointing vector, and the phase velocity, in fact, is not really valued very much, despite the fact it looks really wonderful. So now now the question is, can we mimic left-handed 3D materials? What we saw here so far was just a 2D waveguide as a kind of an example. And the answer is yes, we can. We can fabricate these structures at sub-wavelength scales with some kind of average permittivity and permeability. So here's an example of a 3D structure where instead of just having a 2D waveguide, we now have slabs of alternating materials. And the one I'm starting with here is alternating periodic structure of two different dielectrics. So now we have light that's coming down here in this direction, TiO2 and SiO2, and there's several, I don't know, 5 or 6 slabs here. D1 and D2 are going to be, once again, on the order of some tens of nanometers, maybe up to 100 nanometers. And we'd like to see what happens if we shine light on a structure like this. Well, the way to think about it is, first of all, now we imagine that the light is coming in from the bottom. The light will strike at some angle. Some of the light will reflect, some will penetrate up until it reaches this next interface. At the next interface, some will reflect, some will penetrate. Once again, we get it again. And so we get this constant, we get this sort of zigzag motion as the light starts to propagate up in this direction. Now, there is a vector, a propagation vector associated with the total periodicity of this structure, which is indicated by this expression up here. So this is called the block vector, and it comes from simply getting boundary conditions or matching boundary conditions at each one of these interfaces. So this is a somewhat complicated formula, actually not very much. It says that k, which is the block vector, times lambda, which is the wavelength of the light associated with this periodic structure, is given by this expression here, where k1 and d1 is the width or the thickness of material 1, and d2 is the thickness of material 2, and k1 and k2 are simply the 2 pi over lambda, where lambda is the effective wavelength in each one of these materials which have an index of refraction. I want to emphasize that as this light propagates, it's propagating via real propagating modes. So there's oscillations of light as it goes through in these different directions. Now what happens, what one sees is that in fact there are transmission zones and band gaps of no transmissions with periodic structures like this. So this is what's called a photonic band gap material, or a two-dimensional photonic band gap. And so what we see here is that for large zones of frequency, there is perfectly good transmission, but there's also this zone here where there's no transmission. There's a band gap. And so what this actually looks like, the transmission can be written down in a formula involving k and lambda, there's the block vector and the block wavelength, and the number of layers here, and you get something where you get this is this region where you get no transmission, then it comes back up again. So this is a kind of strange sort of interference. The kind of interference that we're used to thinking about is one where you have wavelets which will either constructively interfere or destructively interfere with the same wavelength. Here we have a whole zone of wavelengths where there's an effective interference throughout this whole periodic structure. Okay, now what happens if we substitute one of the dielectrics for a metal? Now we have TiO2 and silver, and we look at it again. So if we do this again, now we see that we can get coupling from one level to the next, or from one layer to the next, but now it goes by a kind of resonant tunneling through evanescent plasmon modes. So basically what happens here is that you set up surface waves. Now you have because you have a metal and a dielectric, you have surface waves which will set up between these, and the surface waves will move in this direction, but in this direction they fall off exponentially in the z direction. And that exponential fall off is what you see here. So TiO2 silver, TiO2 silver. And you see we're looking at the intensities now, so you see that you just have these exponential signatures, both in the silver than in the TiO2, but they're coupled. And so you get this kind of resonant, evanescent, exponential coupling all the way through. And the Kz in the metal and the Kz, where this is the z direction, in the dielectric are given by these expressions here. Okay, so who cares? Or what does that imply? Well, what that implies is something very interesting. It turns out that under certain conditions, if you have light that comes down, say, at just the right angle, this is plane wave coming down from a source that's up here, it will couple to these layers, and it will couple in such a way that the light will transmit through all of these layers with very high efficiency and then come out here at the bottom with very little loss. So we have the incident layer here, we have an exit layer here, and the number of layers that are inside in this periodic structure is actually quite irrelevant. You could have many, many, many layers, and you would get essentially the same result. So this is what the simulation of this actually looks like. So now we have the light coming in here, and you see that the motion of the light inside these structures is all going in the lateral direction, and there's no motion down here. Although there is pointing vector going down in this direction, that pointing vector is being carried by the evanescent modes, not by propagating modes. And then it comes out down here again at the bottom. Now, in this case, for this kind of situation, where we have the metal structure instead of the metal layers instead of the dielectric, it turns out that this expression for the block vector, you have to substitute hyperbolic cosines and hyperbolic sines for the earlier expressions where we just had real cosines and sines here. Now, there's an interesting implication for that. This is where you get something that starts to be a little bit interesting. Basically, the condition for the transmission through this metal dielectric stack is given, again, this is the same expression here that I just showed on the last slide, but I want to show you what the arguments of these hyperbolic cosines and hyperbolic sines are doing. So this is a plot of wavelength, and this is a plot of this cosine k lambda. It's also a plot of k z1 d1 and k z2 d2. So 1 and 2 correspond to metal and dielectric. So this is what these as a function of wavelength, this comes down here. This is the kz1 d1. The kz2 d2 will cross it right in this point here, and the value of cosine k lambda is above 1 in all regions except right in here. So here it's above 1, here it's above 1. The cosine of a k lambda which is above 1 is a region where you cannot have propagation. But right in here, you can have propagation, and this is this transmission region, which is right at what we saw before. So where we have a crossing between the arguments, the kz1 d1, or the phase of these hyperbolic cosines and sines, is the critical region where you can get transmission through these structures with very high efficiency. Okay. So the lesson is the proper choice of geometry and materials can lead to a near perfect transmission through this periodic stack. Now, are there other interesting properties of periodic stacks? The answer is yes, because this periodic stack, in addition to having a condition or a geometry where you can get very high transmission through the entire stack, exhibits optical anisotropy. And this is what optical anisotropy means. We have light propagates in the xy plane differently than from along the z axis. So we have, this is an expression for how light is constrained by the dispersion equation, or this is sometimes called the isofrequency surface. So this is just writing the same expression in 3 different ways. And the way that I want to concentrate on is this expression down here. So now we have a permittivity. If we imagine that we have a permittivity which is different in the parallel direction and from what it is in the perpendicular direction, then we have an expression for a spheroid which is going to take different shapes depending on these different values here. So if we have an isotropic material, then we have this isofrequency sphere, which means that light propagates in all directions equally, and the allowed propagating values of k will appear on this surface. Now, if epsilon parallel and epsilon perpendicular are both positive but different, then we get an ellipsoid. So in this case, for example, E perp is larger than E parallel. If one of them becomes negative, though, then we get a hyperboloid here, and we can get two kinds of hyperboloids. This is called the two-sheet hyperboloid, and here's the one-sheet hyperboloid. So when the epsilon perpendicular is less than 0. Now I want to emphasize that perpendicular and parallel means perpendicular and parallel to the optical axis. It doesn't mean perpendicular and parallel to these sheets. So the optical axis is the unique axis, which is the z-axis. So E perp means the epsilon, which is in the plane of this structure, and E parallel means the permittivity associated with this axis along the z-axis. So this region here, this hyperbolic region, gives rise to a term which is called hyperbolic metamaterials, and they have attracted a lot of interest lately for a reason which I'll try to explain to you on this slide here. Now, hyperbolic metamaterials increase the rate of spontaneous emission of quantum dipole emitters, and this is called the Purcell Enhancement. Here, once again, is our isofrequency surface. This is, once again, the spherical case where everything is isotropic. And now imagine that we have a dipole which is oscillating in this kind of isofrequency space. So we can see that, K can exist anywhere on this surface, but it cannot go beyond. K cannot be larger than this surface, and the projection of K onto the x-axis can go between 0 and K naught. So the number of K vectors into which the dipole can emit is highly constrained in this kind of situation, and this is actually the conventional situation. So dipole emission into this kind of isotropic space is what we usually encounter. Now, supposing that the dipole emitter is in a hyperbolic surface, and here I've, instead of writing both of them, both of these surfaces, I've just written one down here, the lower one. Now what you see here, the kind of interest here is that the number of K vectors into which this dipole can emit is actually open-ended. It goes without limit, because no matter where I put this K, I can always find a projection onto the X which will permit a propagating mode to go. So this means that the number of emitting modes into which this dipole has to emit into is much, much larger, which means that the result of that is going to be a Purcell enhancement, not in a cavity, or there's going to be a Purcell modification. In this case, it's an enhancement rather than a suppression, when the dipole is close to a surface, and not when it has to be associated with a rather high Q cavity. So the increase in available K states equals the increase in the spontaneous dipole emission rate. Now this kind of finding has actually been put into practice and has been reported experimentally by a number of people, but in particular by this group in Tübingen that Philippe Courtet has been associated with. They reported this in this paper here. So in their case, they didn't use a hyperbolic metamaterial, they just used a metal, but the metal dielectric surface will also add extra modes, and those extra modes then have the desired effect. The interest in the hyperbolic metamaterials is there are a lot more modes than a simple dielectric metal surface will provide. Okay, so the permittivities can be different along different directions. And these stacked layers implement an anisotropic metamaterial with these different permittivities. So the way that you actually calculate these permittivities is given by something called the effective medium effective mean theory. So basically what you say is that the light that comes down here sees a kind of average of the properties of each one of these layers. And so we have a very simple formulas that apply to calculate E perpendicular and E parallel. So in the case of this stack of dielectric silver and TiO2 that we've been talking about, this gives an idea of what the parallel permittivity looks like. It's always quite high and positive, whereas this perpendicular permittivity, as a function of wavelength, goes from positive, so this would be the ellipsoidal isofrequency range, to something which goes through 0 here, and then becomes negative over here. So over here is the hyperbolic range, over here is the ellipsoidal range, and we have something where the epsilon of this particular component, this perpendicular component, goes to 0. So that's kind of interesting. What does that mean? Well, this maximum transition corresponds, in fact, to this epsilon near 0 metamaterial. So the conditions for maximum transmission are the same as for this region where this particular permittivity goes very close to 0. So what happens when an emitting dipole is close to an epsilon near 0 material? Well, there's a couple of things that happen. First thing is basically something which looks like an analogy to the Meissner effect. This is called the Meissner effect for electric dipoles, and this suggestion was proposed by Nader Angeda and his group in this PRL here. Nader Angeda is an electrical engineer at the University of Pennsylvania. So it's well known that if you have a superconductor, then the magnetic field is expelled from the superconductor, and that means that the magnetic field around a dipole, which is above this superconductor, can extend into space up here, but down here, because it's expelled, it has to be scrunched up in this direction, which means it's going to have a much higher gradient here. So the proposal was, supposing if we have an epsilon near 0, that means that the displacement field, which is just epsilon times the electric field, will also experience the same kind of expulsion and also kind of produce a kind of crunching up of the gradient of the electric field below the dipole. What that should do is produce an upward force on this, and so it might be a way of levitating the dipole. This is an actual numerical calculation. This is a kind of artist's conception of what it would look like. But this is real values, and here this is taking a case of where up here epsilon is 0, and then epsilon, well, the permittivity is 0 in space up here, so this is just space, and down here this anisotropic material has these two values here. And you see that indeed the electric field is expelled from this region, and you do see that there really is a higher gradient of the field of the dipole down here than there is above. Okay, so this is for a dipole which happens to be 75 nanometers above a uniform epsilon near 0 material. Now mind you, this is not our stack. This is simply a postulated uniform anisotropic material. So the question would be, will this actually work for the periodic stack as well? In other words, are these mean values of epsilon parallel and epsilon perpendicular okay? And so this is an indication of it might be okay. For the dipole that's perpendicular to the field, perpendicular to the surface, so the dipole is oriented in this direction, we see that there's some indication of these contours being scrunched up here. Here it's a little easier to see, with the dipole is parallel, that these are the contours of equal component of EX, and you see that here, in fact, now down in this direction, down here we have the actual stacked metamaterial, and we seem to be getting the same effect as would have been predicted for a uniform anisotropic material. Okay, so what would that have to do with the Purcell effect? What does an ENZ material do as far as the Purcell effect is concerned? Will it enhance or suppress the rate of spontaneous emission? Well, this is once again our isofrequency curve, and now we solve it for Z, which is going to be the propagation components in the Z direction. What do we see? Now let's ask ourselves what happens when the perpendicular epsilon goes to 0. So when you see epsilon goes to 0, clearly Kz is going to 0, which means that our sphere, which would be our isotropic case will flatten out to a pancake where we have kz is going to be 0, and you can still have kx and ky, but clearly we're going to have many fewer states here than we have here. This is going to flatten to a surface. So that means that it seems to imply that the dipole emission into an electron near zero material appears to be suppressed. And this implies that the Purcell suppression, rather than Purcell enhancement, will be extant in the ENZ spectral region. So here we see that essentially by tuning this light with this kind of metamaterial, we should be able to reach ellipsoidal, hyperbolic, and this electron near zero regime. Okay, so this, what about this, this idea of a strong repulsion force? How strong is that force? I mean, here's this electric field gradient here. We think about this in terms of just a purely classical expression. What kind of force is going to be on this dipole, and how will that compare to, say, the downward force of gravity? Well, if we have, supposing that a dipole was a rubidium atom, what we would find is that for the kind of stack we've been talking about, and with the material values that we've postulated, what we find is that the dipole or the atom would be levitated at about a level of 460 nanometers or so. So this is how the force falls off as a function of distance from the surface, and this is what the gravitational force is on a given rubidium atom. And so you see here that it appears that this kind of epsilon near zero anisotropic periodic stack would produce a levitation force on these atoms. So this is all I'm going to say about this. These last couple of slides are somewhat speculative, and this is a work in progress, so it's not a pat canned story. But the take-home message from this talk would be, after you've forgotten everything else about it, is that first, that left-handed optics can be implemented with a judicious choice of natural materials, that negative permeability is not necessary to demonstrate negative index phenomena, sub-wavelength nanoscale waveguides can exhibit modes with negative index, metamaterials such as periodic stack layers can implement hyperbolic and epsilon near zero isofrequency surfaces, and levitation forces and novel Purcell effects appear to be, can be engineered from these metamaterials. So thank you for your attention, and be happy to answer any questions you might have.
John, can you tell us about the status of the experimental validation of these materials? What has been observed experimentally?
Well, there's two kinds of experiments in the direction of the Purcell effect, Purcell enhancement, or the Purcell factor. Okay, so the first kind of the one class of experiments is with cold atoms. And this is the group of Sebastian Slama and Zimmerman. So what they have showed has been that this is now with a surface which is not a metamaterial but just a metal. They've been able to see an enhancement of the emission rate. Okay, so that's fine. There's another class of experiments which have used quantum dots. The advantage of the quantum dots is that you can get the quantum dots much closer to the surface, and so therefore you should be able to see much larger effects. And there, again, people have observed the effect of the Purcell enhancement and have actually carried out quantitative measurements and compared it with a theory which even goes beyond this mean field theory.
With metamaterials, or with the quantum dots have been put onto metamaterials?
No, not on metamaterials. It's still just a gold or a silver. So no one has done anything with the metamaterials yet. So.
John, there are plenty of interesting things in what you present, but when I saw the result about the possibility of having a wideband transmission or reflection. It's two are possible in a series of stacks. Isn't that something that people who are producing the fantastic layers for optics have known for a long time? This morning I cited these people in Philips. I mean, it was long ago, and they were fantastic people. I mean, you were asking a broadband mirror on a wavelength from this to that, and they would produce dozens of layers, and at the end it would work.
Yeah.
Is it different, or is it the same kind of idea?
I think it's the same kind of idea. The interest here, I think, is that you get this very high transmission at the same time that you have this anisotropy. And I think it's the anisotropy which gives rise to these quantum effects, or these new kinds of repulsive forces, which make the experiment, the idea of doing experiments in this regime, an interesting proposition. So as far as I know, the efficient transmission of light through alternating stacks of dielectrics and metal is something which is not new, but it hasn't been appreciated in the sub-wavelength regime.
Okay.
What that means in terms of the hyperbolic regime of the metamaterial, or the epsilon near zero regime of the metamaterial.
Okay, I have another question, if I am allowed. In this counterintuitive behavior of things going in the wrong direction, so to speak, did you try to make a calculation in the spirit of a famous Hall calculation by Sommerfeld, where you look at the transient, you start with echelon function times monochromatic something, okay? And he just looked at the propagation in an ordinary dielectric medium, and there are plenty of interesting things which happen when you have this leading edge, and then you have a component propagating at the velocity of light in vacuum, although you are in a dielectric. This is what he calls the forerunners. And then there is, well, maybe it's a Brillouin calculation of Brillouin, which we find in the book of Sommerfeld of optics. But anyway, I remember I read it in the book of Sommerfeld, okay? And it's extremely interesting. So it's an alternative to the usual calculation for the group velocity, where you take a wave packet or something like that. Here, you have a sudden rise of a front, you have a front, okay, an edge, and then you see what happens. Did you try a calculation?
No, we didn't try anything like that. If you have a sudden edge, that means that you're going to introduce a very broad band in K space.
Yeah, sure. And there is plenty of technicality in the calculation, integration in the complex plane, and things like that.
Yeah.
But they find the solution.
Well, yes. But did they do this in dispersive material?
Yes, they do it in the ordinary Selmayr-like formula of
Okay.
the ordinary Lorentz electron, and with a dispersive and an absorptive term, and they look at what happens.
Okay. Well, I was not aware of this.
It's a beautiful calculation.
Yeah.
It's a beautiful calculation.
Yeah. In this case, this is somewhat similar. This is basically one single frequency.
Yes.
But it's within and there is this domain, and it's the dispersion diagram of the waveguide is really all you need in order to understand what's going on. But if you have a reference, or if you can point me in a direction of what these other
I'm
papers,
sure
I'd be happy to
Moises
take a look
knows
at
it. It's a book of Sommerfeld, Optics, which probably was published first in German, but you have an English translation, you have a French translation, and probably many other languages.
This is
Maybe
part of-
even
this is part of
Portuguese, who knows? Huh?
This is part of Sommerfeld's physics course.
Exactly.
Yeah,
It's
okay.
a volume on optics.
Okay.
It's a beautiful calculation.
Okay. If not, I guess we can thank John and all the speakers of the afternoon again.